Back in action. This is question 13. A little bit confusing because they don't give you actual numbers here to work with. The formula is straightforward enough. We're saying the weight at time t equals the initial weight times 2 to the power of minus 000 whatever. I'm seeing an equation like that. Hopefully you know what that looks like. It's really very similar. I've got some number here, this initial weight. And then we've got some negative power. If I was to simplify it like that, you know what a normal exponential looks like, as in, you know, this type of shape. Right, this would be, I'll use x here, x's and y's. And so what would happen if we come along and do a minus? The reason I'm going through this is actually just to get you to see the shape graphically. It can be very useful to be able to think graphically. Now, all of these x's are now negative. If they were positive, and all the negative x's are now positive, so it's like we get this reflection here about the y-axis. We're now looking at something like that. We're dealing with time, so we're only interested in this quadrant here, and I'm interested in the shape, right, that I'm getting here. So whenever you see minus powers in a question like this, it's not a growth question, it's a decay question, right? Which comes from the shape. We've got time and we've got some weight of our radioactive substance. We've got some initial weight, and then that weight is decaying down, right? This question wants to know, if we started here, how long, right, before we get to quarter? Excuse me, let me fix that. So it's like, what time do we get to a quarter of the original weight? Here, right? So what is this time? Okay, so hopefully you know all that when you see an equation like this before you start a question like this. In this question they're saying when they want the actual weight at time t to be a quarter of the original weight, and they don't tell you the number. You know, if they told me it was 1,000 grams or something, I could work out a quarter and say it's 250, but they don't do that. So what I thought was, let's call that initial weight, just give it some label, W, right? And I think, well, how could we express the weight that we're looking for in terms of W? So we need it to be a quarter of W, right? We need to take the initial weight and quarter it. So if I've labeled my initial weight as W, I mean, I could give it another label. Maybe I could do this slightly differently. Maybe I could have said let W of t equal x or something, right? And then I could have said the initial weight's 4 times that. But you know, you've got to find some way to do this. So therefore, I could rewrite my formula and I could say I'm looking for a quarter of this original weight, which I've labeled W. It's been W times 2 minus 0.030. Oh, let me tidy that up for you. 0.0002. This decay is going to be quite slow, which can often happen with radioactivity. So, you know, and now we've got something to work with. And at this point, I can actually just think about cancelling these out, because I know that the weight is just some number, right? I don't have to think about it as possibly equaling 0, or is, you know, this is just some weight, like 1,000 grams or something. It's on both sides of the equation, so we can just cancel it out. Right? We can apply log laws. Say log a quarter equals log of 2 to the power of minus 0.0002t. We've got that log. We can use our power rule, minus 0.0002t log 2. Right, we're dealing with powers, so we can multiply. This log a quarter, we might want to actually say that, you know, the log, I've been through this in class. The book will often write logs, if they're a fraction, you know, we can write it like this and say it's a negative answer. You know, so that this log, to give the answer of 1/4 in base 10, obviously, you need a negative power to do that. So you can write this as a negative to begin with. And the reason I'm looking to do that here is because I had a negative over there, and I thought, well, it'd be nice to cancel those negatives out. You know, we could multiply both sides by -1 and just deal with positive numbers. Right. So, not that you have to. That's up to you. So with a bit of rearranging, I'm trying to get t equals, right? So I need to take my log 4, divide it by log 2, right? I'm trying to get the t by itself. The t's also been multiplied by 0.0002, so I need to divide by that as well. But this is something your calculator can do fine. And then we'll have our answer for t. Just be careful in the calculator, you need brackets here, right? So that you divide log 4 by everything and not just the log 2. So if I go to the calculator now, we'll find out the answer. We've got log 4. By the way, I've used logs in base 10. I could have used natural log. We use natural log so much in this course. If you get used to using that, you can use it here in a question like this. 0.0002, count these up, and notice that I'm putting all of this divisor in brackets here, what I'm dividing by. So the answer is 10,000. I assume this was in years, right? Yeah, t years. Okay. So to finish that question, bring the units back in. Whenever you've got a real-worldy type question, that's where units are going to become important, like when we're doing kinematics and we want to know if it's in meters per second squared, right? So as soon as they start trying to model a real life situation, make sure that you actually write in years. And if you were graphing, right, your labels, people, don't write x there, write t for time in brackets. Time is in years. Okay, and I was saying in the previous video with logs, I was saying, you know, don't let the markers take marks off just because you're not drawing arrows or labeling things properly. it's kind of frustrating marking tests and taking marks off for little things like that.